So this section is going to be a lot of derivative rules, and what I highly recommend doing is having some separate piece of paper available to collect these rules on so that you can refer back to it. Because everything we've done so far has been relying on that difference quotient. So to take the derivative of a function, we've been evaluating this limit of f of x plus h minus f of x all over h, which, depending on how complicated our function f of x was, required a lot of work and a lot of algebra. And what ends up happening is a lot of themes come through. Like in this video, we're going to look at the power rule, which is going to be when we have exponents. There's a theme that comes through of how we treat exponents within derivatives. And with that, we can rely on this rule instead of having to take the difference quotient every time. So we're going to get some shortcuts to our calculations here, and then we can rely on these for finding our derivatives. Just as a refresher of our notation and what I'll be using, so like f prime of x, so that's the derivative of f of x. Some similar notation is this d dx, and if, let's say I put f of x in there, these are the same exact thing. This is the derivative of f of x. This is the derivative of f of x. So, same thing. Typically, I'll stick to this notation for kind of solving for our function. And then in terms of showing these rules working and applying it to different parts of our function, I'll be using this notation. So you'll see a mixture of the two. So I'm going to go a little fast through these first rules because they're pretty quick, and especially if we think about the graph and how it all comes down to the derivative. Again, it's the slope of the tangent line. So if we can tie it back to that, that can be helpful with some of these. So if our function is a constant, which means in terms of a graph, this would be just graphing a horizontal line. So imagine if I said, okay, here's a point right here. What's the tangent line? Well, the tangent line just lands right on top. And the slope of that tangent line is flat, just like the original function, which means we have a slope of 0. So if we take the derivative of a constant, because it has this behavior of just a flat line, the derivative is equal to 0. So if we have a function f of x, and we want to take the derivative, so if I wanted to find f prime of x, that's coming from taking the derivative d dx of that value of 5. And when we do this, taking the derivative of a constant number is just equal to 0. So f prime of x is equal to 0 when we take the derivative of that number 5. All right, a linear function, which would have mx plus b. So let's say I graph a linear function. So I'm graphing a line, and let's say I choose a spot somewhere. And I say, graph the tangent line at that spot. Well, with the linear function, it's going to match up. It's going to graph right on top of our linear function. So if I wanted to know the slope of that linear function, it's going to just match the slope of that original line. So with a linear function, we have some slope, and if we want to find the slope of the tangent line anywhere on that line, it's going to be equal to the slope. So if we take a derivative here, you end up with just the slope. So if I'm taking the derivative of this function 2x plus 1, so if I'm taking the derivative of 2x plus 1, what I can do is recognize that that's linear, and all we're going to have left over is the value that's multiplying with x, because that would be our slope. So this will be f prime of x equals 2. So those are just some first rules that we want to keep in mind. If you take the derivative of just a number, you end up with 0. If you take the derivative of just a number times x, that kind of behavior is like a slope of a linear function, and you'll just be left with that number that's multiplying with x. The power rule. So if we have x with some exponent, what we do when we take the derivative is the exponent comes out front to multiply, we bump that exponent down by 1. So we're going to end up with the exponent times the base raised to an exponent minus 1. Let's try that out. So I'm going to start with this f of x equals x cubed. I'm going to keep some of my derivative notation in there just so that you get used to seeing it. Some of these rules we'll really get the hang of, that we'll use kind of shortened notation here and there, but just during this kind of introduction to it, I'm going to keep it in there. So taking the derivative, I want f prime of x, so I am taking the derivative of x cubed. And to take the derivative, what we're going to do is two things with the exponent. It's going to come out front to multiply, and in the exponent, it's going to bump down by 1. So exponent of 3 comes out front to multiply. We keep that base of x, and then the new exponent, 3 minus 1, 2. So the derivative of x cubed is 3x squared. And we're done. That would be our derivative function. So this is a function that is graphing all of the numerical values for the slopes of the tangent line to x cubed. All right, let's get some review of two exponent rules. In fact, I'm going to do h of x first. So we're going to review negative exponents and, ran out of room, and rational exponents. I just wanted to note this so that if you wanted to look them up on Khan Academy or wherever you can. So yeah, I'm going to start with h of x, which is the 1 over x cubed. So I can't use the power rule here because my base with the exponent is in the denominator, and to use this power rule, it needs to be up in the numerator. So basically, I want a way of taking this x cubed and moving it up to the numerator, which this whole like moving between numerator and denominator is exactly the function of the negative exponent. So this function h of x, where it's written as 1 over x cubed up above, is the same exact thing as x to the negative 3 power. So that negative exponent means like, it really should be down in the denominator to have the positive exponent. So we're switching between negative and positive, and it just changes the location. Now I have base and exponent, and I can use the power rule. So taking the derivative of h of x equals that exponent of negative 3 is going to come out front. I'm going to have negative 3 times x, and then the exponent, we're going to have a negative 3 minus 1, which is just a negative 3 times x to the negative 4 power. And typically we want to end with all positive exponents, so I just want to simplify this. And something that's important to keep in mind is that negative 3 is separate. It's not underneath that exponent. So negative 3 isn't going to move anywhere. That negative 3 stays put, but that negative exponent on x is going to move x to the denominator, and now we can have a positive 4 exponent. So negative 3 stays in the numerator. X, because it has a negative exponent, moves to the denominator, and that negative exponent becomes positive. So the derivative is negative 3 over x to the 4th power. All right, and I'm going to go back to that g of x where we have a rational exponent. So square root of x. The rule with rational exponents, so say we have some type of root of x, and x could even have an exponent on it. So say we were taking the nth root of x to the m power. This is the same thing as x to the m divided by n power. So the exponent makes the numerator, the level of root that we're taking makes the denominator. So when we take a square root, it's like we're taking a level 2 root. X really just has an exponent of 1 on it. So what I want to do is rewrite this so that I can use the power rule as x to the 1/2 power. And now I can use the power rule. So if I take the derivative of g of x, that exponent of 1/2 comes out front, 1/2 times x, and then we'll have 1/2 minus 1. So the derivative is equal to 1/2 times x. And then 1/2 minus 1 is a negative 1/2. All right, and there's our negative exponent, so we need to simplify. So again, this 1/2 stays exactly as it is. So 1 stays in the numerator, 2 stays in the denominator, and then for this x to the negative 1/2 moves to the denominator so that it's a positive 1/2. And then just changing it back to a square root, we're going to have 1 over 2 times square root of x. And we're done. So some review of rational and negative exponents in there. All right, so that's our power rule, which is a big foundation for this section. But we have these little rules around it too, so that eventually we can take the derivative of these different polynomials. So let's go to this constant multiple rule, which if you look at our example functions here, so like 3x squared and 1/2 x, what we're adding in is a number that's multiplying with x on the outside when we take the derivative. And what we do is when we have a constant multiplying, essentially like part of the function, is that the constant just keeps multiplying out front. So if we have this f of x equals 3x squared and I want to take the derivative, so what this would look like is I'm taking the derivative of 3 times x squared, and what we'll do is that 3 that's multiplying will just stay multiplying out front. And then what I can do is focus on the power rule for the x squared portion of that. So using the power rule, that 2 is going to come out front to multiply, and we're going to bump it down by 1. So exponent of 2 comes out front to multiply, so we're going to end up with a 3 times 2 out front times x, and then the exponent 2 minus 1 is an exponent of 1. So that derivative is equal to 6x. So how I eventually think about it, instead of these separated steps, is I just do that multiplication in one step. So that 2 comes out front to multiply, so 3 times 2 is 6, and then bumping down that exponent by 1. All right, let's look at g of x here. So taking the derivative of g of x, so that 1/2 is going to stay there. And then actually this ties back to our linear functions rule. Like this would be a linear function where you have a slope of 1/2, which means we're just going to be left with the slope. So actually we're already done because those rules tie together and we would just have that left as the derivative. If you by some chance applied the power rule to it, which is absolutely fine too, so that exponent of 1 would come out front times x, and then we would have a 1 minus 1 power. I'm just going to go with this, but we could have been done at just that 1/2. So 1/2 times 1 is 1/2. 1 minus 1 is a 0, and when we have a power of 0, anything raised to a power of 0 is equal to 1. So this is just a 1/2 times 1. So that would also simplify to 1/2. So you don't have to apply the power rule. You can just know that when you have x with a power of 1, it's going to change into a 1 when you take the derivative, because essentially you're just being left with a slope. All right. Addition and subtraction. If we have a bunch of different things adding and subtracting with each other and we want to take the derivative of that string of addition and subtraction, that addition subtraction acts as a separator, so you can just focus on the derivative of one function at a time as they're separated by addition and subtraction, which is such a nice rule. So let's try this out. We have this big function here, 17x to the 10th plus 13x to the 8th minus 1.8x plus 1003. And we want to take the derivative. So what this is going to look like, kind of a long written out form, is that we're going to take the derivative of 17x to the 10th, and then we'll have plus the derivative of 13x to the 8th minus the derivative of 1.8x plus the derivative of 1003. And this is going to be a lot of that constant multiple and power rule together. So we get to just focus on one piece at a time. Take your time with these. All those little mistakes will come up if you try to go too fast. So just look at one term at a time. So here we have 17x to the 10th. So that 10 is going to multiply with 17. In fact, I'm going to go ahead and take a step to write that out. So we're going to have 17 times exponent of 10 times x, and then that exponent's going to be a 10 minus 1, so an exponent of 9. And then we'll have plus 13x to the 8th, so we'll have 13 times that exponent of 8 times x, and then 8 minus 1 will leave us with an exponent of 7. And then minus, this is where we have x with an exponent of 1, and we're just going to be left with that constant. Or again, if you think of it as the slope, we're just left with that slope. And then the derivative of a constant, which we have at the end here, just turns into a 0. So we end up with, let's go ahead and simplify this. So 17 times 10 is 170, x to the 9th, plus 13 times 8, which is 104, x to the 7th, minus a 1.8, and we took the derivative. Okay, for just a moment, imagine if you had to do that with the difference quotient, plugging in x plus h into each of those pieces and expanding it out. It would take so long, so long. So this is where the power rule really saves us a lot of time and a lot of headaches. Okay, let's do this one here. F of x equals 2x to the 7th minus 5 over root x minus 8. So my first step here, what I'm going to do is adjust this root x that's in the denominator there so that it's power form. So we're going to have 2x to the 7th minus 5. So this is an x to the 1/2 in a denominator. So I'm going to move it to the numerator, which means I'd have to have a negative exponent. And then because it's a square root, negative 1/2. And then minus 8. So this is going to stay true each time. If you have a square root in the denominator, it's going to be a negative 1/2 in its exponent form. All right, taking the derivative. And I'm just going to go ahead and start applying the power rule. So 7 times 2, and I'll write out this step. So we'll have 2 times that exponent of 7 times x, and then a 7 minus 1 will leave us with an exponent of 6, minus 5 times that exponent of negative 1/2 times x, and then negative 1/2 minus 1, so that's going to be a negative 3/2. And then at the end, there would be a derivative of a constant, which just turns into a 0. So we won't have anything else there. All right, let's simplify. So 2 times 7 is 14, x to the 6th. Then we'll have, let's see, negative times a negative, so we'll have positive 5/2. And then x to the negative 3 over 2. Let me just show you some side work here of how this is gonna go. X to the negative 3 over 2. So take care of the negative first, which just puts it in the denominator. Now, when we have a rational exponent, denominator is telling us about the root, and the numerator is telling us about the exponent. So, changing this, it'll be 1 over, it's a square root, and there'll be x cubed. So, that x to the negative 3 over 2 is going to look like 1 over the square root of x cubed. So, if I have this 5/2, the 2 in the denominator, that square root of x cubed will be in the denominator. And that's done. All right, this video is getting long, but we just have a few more questions here to go through. So specifically finding the equation of the tangent line, and we're also going to look at a word problem real quick. So whenever you're asked for the equation of a tangent line, you're looking for y equals mx plus b, where you want to find a slope and an intercept. And the slope ties to the derivative. So we're going to find the slope first, and then we can find our y-intercept. So we have our function 10 minus t squared, and we're looking at when t is 2. What's even better, if they give you an input value, you'll end up wanting the full coordinate. So like when t is 2, let's go ahead and see what happens when we look at g of 2. So that would be 10 minus 2 squared, which is 10 minus 4, which is 6. So really we're looking at this coordinate 2, 6 on this 10 minus t squared function. All right, first step. What we're going to do is find the slope. So we're going to be taking the derivative at this point. So we have g of t, I'm going to go ahead and rewrite it. G of t equals 10 minus t squared. So taking the derivative, so we can think about taking the derivative of each term as we're going through. So derivative of 10 is just 0. Derivative of a constant, 0. Derivative of this negative t squared, we'll use the power rule, so we'll have this negative hanging out front. Exponent of 2 comes down, t, and then exponent of 2 minus 1, which would just be an exponent of 1. So our derivative function is negative 2t, and what we're going to do is look specifically when t is equal to 2. So g prime of 2 equals negative 2 times our input of 2. So our slope at t equals 2 for the tangent line is a negative 4. So that right there is our slope. So then what we can do is go ahead and look for the intercept. And what we have so far, so we have y equals, we found m is negative 4 and then x plus b. And what we're going to do is plug in the coordinate so we can figure out what the y-intercept should be. Because what we have right now is we have the slope working for our tangent line. What we need to figure out is its placement so that it goes through this coordinate on our function. So y is 6, x is 2. So 6 equals negative 4 times 2 is negative 8. And add 8 to both sides, so b is equal to 14. So the equation of our tangent line is y equals negative 4x plus 14. And let's take a look at that graph. If I can find my screen. There we go. All right. So in red here we have 10 minus x squared, so that's this upside down parabola. And we were looking at this coordinate 2, 6. I'm trying to fit the tangent line to it. So this green line, this negative 4x plus 14, what we can see is it's going through that coordinate 2, 6, and then the slope is working so nicely to just touch at that point, and if we zoom in, they look like the same line because they're matching in terms of slope. So what we did is we matched that instantaneous rate of change, and then we were able to choose find a y-intercept such that it went through that coordinate 2, 6. Okay, one quick little word problem here, which I know is probably not a great thing to hear when we hear word problems, but we'll make it real quick. Our function is nice and simple with the square root of x, and that'll calculate cost. So we're looking at x equals 100, and then we'll look at x equals 101. And then we want to find, there's a lot of typos there. What is the cost of the 100 first item, which will just be the difference in those two. So when x equals 100, the cost is square root of 100, which is 10. That's $10. When x equals 101, so we'll take the square root of 101. And I'm going to go ahead and include a lot of decimal places here, but this would be $10. And then I'm just going to include all of these so that we get a good comparison with our next question. So the cost of the 100 first item is pretty much 5 cents, but it's really 0.04987,562. Okay. So this is getting at the idea of how we calculated marginal cost in our pre-calculus class. But now with calculus, we can get a more accurate value for this marginal cost because it ties to instantaneous rate of change, which ties to derivatives. So if we have f of x equals the square root of x and we want to find the derivative, so f of x equals square root of x is the same thing as x to the 1/2 power. Taking the derivative, so we will have 1/2 comes out front, x, and then 1/2 minus 1 will give us an exponent of negative 1/2, which means our derivative function is a 1 over 2 times square root of x. So we want to evaluate this at 100, which is the idea of looking at the marginal cost at 100 items. This is going to be a 1 over 2 root 100, which is just 1 over 2 times 10, which is 0.05. So how does this compare to part A? Now we're saying the marginal cost is 5 cents exactly, and this is more accurate using the derivative this exact moment instead of kind of leapfrogging across these different points and then looking at the difference. So they represent the same thing. This is just a more instantaneous focused in value rather than comparing across two numbers.